Hi, I'm Sanjana Reddy, a machine learning engineer at Google's Advanced Solutions Lab. There's been a lot of excitement around generative AI and all the new advancements, including new Vertex AI features that are coming up, such as GenAI Studio, Model Garden, GenAI API. Our objective in this short session is to give you a solid footing on some of the underlying concepts that make all the GenAI magic possible. Today, I'm going to talk about transformer models and the BERT model. Language modeling has evolved over the years. The recent breakthroughs in the past 10 years include the usage of neural networks to represent text, such as word-to-vec and n-grams in 2013. In 2014, the development of sequence-to-sequence models, such as RNNs and LSTMs, helped improve the performance of ML models on NLP tasks such as translation and text classification. In 2015, the excitement came with attention mechanisms, and the models built based on it, such as transformers and the BERT model. In this presentation, we'll focus on transformers. Transformers is based on a 2017 paper named Attention is All You Need. Although all the models before transformers were able to represent words as vectors, these vectors did not contain the context, and the usage of words changes based on the context. For example, bank in riverbank versus bank in bank robber might have the same vector representation before attention mechanisms came about. A transformer is an encoder-decoder model that uses the attention mechanism. It can take advantage of parallelization and also process a large amount of data at the same time because of its model architecture. Attention mechanism helps improve the performance of machine translation applications. Transformer models were built using attention mechanisms at the core. A transformer model consists of encoder and decoder. The encoder encodes the input sequence and passes it to the decoder, and the decoder decodes the representation for a relevant task. The encoding component is a stack of encoders of the same number. The research paper that introduced transformers stacks 6 encoders on top of each other. 6 is not a magical number, it's just a hyperparameter. The encoders are all identical in structure, but with different weights. Each encoder can be broken down into 2 sublayers. The first layer is called the self-attention. The input of the encoder first flows through a self-attention layer, which helps the encoder look at relevant parts of the words as it encodes a center word in the input sentence. And the second layer is called a feed-forward layer. The output of the self-attention layer is fed to the feed-forward neural network. The exact same feed-forward neural network is independently applied to each position. The decoder has both the self-attention and the feed-forward layer, but between them is the encoder-decoder attention layer that helps the decoder focus on relevant parts of the input sentence. After embedding the words in the input sequence, each of the embedding vector flows through the 2 layers of the encoder. The word at each position passes through a self-attention process. Then it passes through a feed-forward neural network, the exact same network with each vector flowing through it separately. Dependencies exist between these paths in the self-attention layer. However, the feed-forward layer does not have these dependencies, and therefore various paths can be executed in parallel while they flow through the feed-forward layer. In the self-attention layer, the input embedding is broken up into query, key, and value vectors. These vectors are computed using weights that the transformer learns during the training process. All of these computations happen in parallel in the model in the form of matrix computations. Once we have the query, key, and value vectors, the next step is to multiply each value vector by the softmax score in preparation to sum them up. The intuition here is to keep intact the values of the words you want to focus on and leave out irrelevant words by multiplying them by tiny numbers like 0.001, for example. Next, we have to sum up the weighted value vectors, which produces the output of the self-attention layer at this position for the first word. You can send along the resulting vector to the feed-forward neural network. To sum up this process of getting the final embeddings, these are the steps that we take. We start with the natural language sentence, embed each word in the sentence. After that, we perform multi-headed attention, 8 times in this case, and multiply this embedded word with the respective weighted matrices. We then calculate the attention using the resulting QKV matrices. Finally, we concatenate the matrices to produce the output matrix, which is the same dimension as the final matrix that this layer initially got. There's multiple variations of transformers out there now. Some use both the encoder and the decoder component from the original architecture. Some use only the encoder, and some use only the decoder. A popular encoder-only architecture is BERT. BERT is one of the trained transformer models. BERT stands for bidirectional encoder representations from transformers and was developed by Google in 2018. Since then, multiple variations of BERT have been built. Today, BERT powers Google search. You can see how different the results provided by BERT are for the same search query before and after. BERT was trained in 2 variations. One model contains BERT base, which had 12 stack of transformers with approximately 110 million parameters, and the other, BERT large, with 24 layers of transformers with about 340 million parameters. The BERT model is powerful because it can handle long input context. It was trained on the entire Wikipedia corpus and books corpus. The BERT model was trained for 1 million steps. BERT is trained on different tasks, which means it has multitask objective. This makes BERT very powerful. Because of the kind of tasks it was trained on, it works at both a sentence level and at a token level. These are the 2 different versions of BERT that were originally released. One is BERT base, which had 12 layers, whereas BERT large had 24 layers, and compared to the original transformer, which had 6 layers. The way that BERT works is that it was trained on 2 different tasks. Task 1 is called a masked language model, where the sentences are masked and the model is trained to predict the masked words. If you were to train BERT from scratch, you would have to mask a certain percentage of the words in your corpus. The recommended percentage for masking is 15%. The masking percentage achieves a balance between too little and too much masking. Too little masking makes the training process extremely expensive, and too much masking removes the context that the model requires. The second task is to predict the next sentence. For example, the model is given 2 sets of sentences. BERT aims to learn the relationships between sentences and predict the next sentence given the first one. For example, sentence A could be, "A man went to the store," and sentence B is, "He bought a gallon of milk." BERT is responsible for classifying if sentence B is the next sentence after sentence A. This is a binary classification task. This helps BERT perform at a sentence level. In order to train BERT, you need to feed 3 different kinds of embeddings to the model. For the input sentence, you get 3 different embeddings: token, segment, and position embeddings. The token embeddings is a representation of each token as an embedding in the input sentence. The words are transformed into vector representations of certain dimensions. BERT can solve NLP tasks that involve text classification as well. An example is to classify whether two sentences say, "My dog is cute and he likes playing," are semantically similar. The pairs of input texts are simply concatenated and fed into the model. How does BERT distinguish the inputs in a given pair? The answer is to use segment embeddings. There is a special token, represented by SEP, that separates the two different splits of the sentence. Another problem is to learn the order of the words in the sentence. As you know, BERT consists of a stack of transformers. BERT is designed to process input sequences up to a length of 512. The order of the input sequence is incorporated into the position embeddings. This allows BERT to learn a vector representation for each position. BERT can be used for different downstream tasks. Although BERT was trained on masked language modeling and single sentence classification, it can be used for popular NLP tasks like single sentence classification, sentence pair classification, question answering, and single sentence tagging tasks. Thank you for listening. Hi, I'm Sanjana Reddy, a machine learning engineer at Google's Advanced Solutions Lab. Welcome to the lab walkthrough for transformer models and BERT model. In this lab walkthrough, we'll be going through classification using a pre-trained BERT model. You'll find the setup instruction in our GitHub repository. Let's get started. In order to work on this notebook, you'll need to log into Google Cloud, go into Vertex AI, and click on Workbench. Make sure that you have a notebook created. Once the notebook instance has been created, click on Open Jupyter Lab. Once you've followed the instructions in our GitHub repository, navigate to Classify Text with BERT. In this notebook, we're going to learn how to load a pre-trained BERT model from TensorFlow Hub and build our own classification using the pre-trained BERT model. We'll learn how to train a BERT model by fine-tuning it. Before you get started, note that this notebook requires a GPU because the training does take quite a bit of time. When you open this notebook, there is a setup instruction in order to set up a BERT kernel to install all the required libraries for this notebook. For this notebook, we're going to be using TensorFlow and TensorFlow Hub, TensorFlow Text, which is required to pre-process the input for the BERT model. You can see that I'm checking if a GPU is attached, and I see that I have one GPU attached to this notebook. In this notebook, we're going to train a sentiment analysis model to classify movie reviews as either being positive or negative based on the text of the review. We're going to be working with the IMDb dataset that you can download from this URL. Once we have downloaded the dataset, we can examine the data to see what's in it. We see that we have 25,000 files that belong to two classes, positive and negative, and we're going to be using 20,000 files for training and the remaining 5,000 for testing. A sample of this dataset shows you the movie review over here and an associated label. So for the one over here, we see that the label that is associated is negative, and the one below here, it's positive. Once we've examined our dataset and we're happy with it, we're going to load a pre-trained BERT model from TensorFlow Hub. TensorFlow Hub offers multiple different variations of BERT models in all different sizes. We're going to use a small BERT for today's notebook. So this BERT model has 4 different layers. It has 512 hidden units, and it has 8 attention heads. For every BERT model that we load from TensorFlow Hub, it is associated with a corresponding pre-processing model. You can find the corresponding preprocessing model on TensorFlow Hub as well. We're going to examine the preprocessing model. So we're going to load the preprocessing model we see in the previous step, and we pass a sample text over here. So we just pass, "This is an amazing movie," and we're going to examine the output. The preprocessing model gives us multiple outputs. The first is the input word ID. The input word ID is the ID of the words in the tokenized sentence. The preprocessing model also provides us the masking for each word. Every sentence is converted into a fixed length input, and it masks words that are not valid. So once we have preprocessed our input text, we can use the loaded BERT model from TensorFlow Hub. In this particular cell block, it doesn't really make any sense because we've not trained the model. This is just a random list of numbers at this point. But once you pass the preprocessed text into this BERT model, you get certain embeddings. So in order to define our classification model, we start with an input layer. The input layer takes the raw text as input, passes it on to the preprocessing layer for preprocessing that converts it into token IDs, word IDs, and mask IDs. The preprocessed words are then passed to the pre-trained model. There is an argument here called trainable. Trainable here determines if you want to fine-tune the pre-trained model using the new data that you're training with or not. In our example, we are setting trainable to true, which means that we're going to update the initial weights of the pre-trained model. Your decision to set this to true or false depends on two things: whether you want to update the weights, and second, on the size of your dataset. If you have a relatively small dataset, it is recommended to set this to false so that you're not introducing noise into the pre-trained weights. But if you have a large enough dataset, you can set this to true. Once we have our pre-trained model, we pass it through a dense layer to get probabilities for each of our classes. This is what the output from the model is going to look like. The output is going to be a probability of whether this particular sentence is positive or negative. Since we're working with a binary classification problem, we're going to use binary cross-entropy as our loss function, and the metric to optimize for is going to be binary accuracy. We're initializing our training by defining the optimizer. In our case, we're using Adam, which is a popular choice for neural network models. Once we've initialized the training, we can start training using model.fit. We can pass the train dataset and the validation dataset and the number of epochs that we want to train for. Once the model has trained, let's evaluate the performance of the model. So in our case, we see that the model achieved an accuracy of 85%, which is pretty decent considering we only trained it for 5 epochs. You can potentially plot the accuracy and loss over time in order to visualize the model's performance. We see that the training loss is going down, and we could work on our validation loss a little bit, but for the sake of demonstration, we've only trained it for 5 epochs. Once you're satisfied with the model that you've trained, you can save the model using model.save. Model.save exports your TensorFlow model to a local path. So the export path in this line is going to be a path in your notebook instance. Once you've saved your model, you can load it to get predictions. So in this example, we have, this is such an amazing movie, this movie was great, the movie was okay-ish, the movie was terrible. And we get predictions for each of these sentences based on the model that we have trained. If you would like to take this further and deploy your model on Vertex AI to get online predictions, you could take the locally saved model and export it to Vertex AI. In order to do this, you need to check the signature of the model to see how you can pass predictions to the model. The signature of the model shows you what is the first layer that is taking input. So once we have the locally saved model, we are going to push the model to Vertex's model registry using these commands. In order to put the model in Vertex's model registry, you need to ensure that you have a Google Cloud Storage bucket, and these lines over here let you create a bucket if it doesn't already exist. We're going to copy the locally saved model using gsutil-cp, which takes the locally saved model from the export path and puts it in the Google Cloud Storage bucket. Once the model is in the Google Cloud Storage bucket, we're going to upload it to Vertex AI's model registry. We're using the Python SDK in this case, so we have aiplatform.model.upload, which takes the model from Google Cloud Storage bucket and puts it in the model registry. Once the model has been uploaded, we're ready to deploy the model on Vertex and get online predictions. In order to do this, we can use the Python SDK again. So we can use uploadedModel.deploy, which is a function that is going to do two things. One, it's going to create an endpoint, and two, it's going to upload the model to this particular endpoint. So you can see here that it's creating the endpoint, providing you the endpoint location, and then once the endpoint has been created, the model is deployed to this endpoint. This step is going to take around 5 to 10 minutes when you run through your notebook, so just don't worry if it takes too long. Once the model has been deployed to the endpoint, you're ready to get predictions from this endpoint. So you can create an instance object. So using the signature of the model, we know that the name of the first input layer is text. So we're going to pass our review text to this particular key. We create this instances object that is going to be passed to the endpoint.predict function. And the endpoint.predict function is going to take this instance and it's going to give us predictions. So we can see for our first instance, I love the movie and highly recommend it. We have a prediction of 0.99. For it was an okay movie, in my opinion, we have 84%. And for I hated the movie, we have 2%, which means it's a negative sentiment. So this is how you can create a classification model from a pre-trained BERT model and then deploy it on Vertex to get online predictions.